Hey there again. So last lesson you learned about exponential growth and decay, and in most of those situations you were always given some sort of growth rate or decay rate, and most of those were given to you as percentages, which you then converted to growth or decay factors. In today's lesson, we're just going to extend that to some special situations that are very, very commonly seen in real life scenarios, things where we're talking about bacteria or infectious disease that grows at such, well, think about the coronavirus. At what rate is that growing? Extremely, extremely fast. That's an example of, it's a perfect example, a real life example of something that's, and I don't actually know this number, but how quickly is it growing from what it was previously? So when we talk about doubling life or doubling time or half-life, we're talking about how long it takes. So the length of time that it takes something to double in its size. So oftentimes it's easier to compare it to an original point and say, it took 7 years for it to go from 50 cases to 100 cases. Or in coronavirus's case, it took 5 hours to go from 100 cases to 200 cases. And so if you're talking about a doubling time, it's basically asking you for a length of time it takes something to double in its size. Or on the contrary, if it was a half-life, you were describing how long does it take for something to decrease to exactly half of what it originally was. Now you can calculate a half-life or doubling life at any point in the duration of the event, but it's usually easier to compare it to the original quantity. Okay, now the formula you're going to use is exactly the same as before, y equals ab to the x. That formula is not going to change. It's still exponential, so we're still dealing with, the standard basic formula. But in this case, we don't have a percentage, which means we don't have to have a growth factor. It's always going to be either 2 for a doubling time or a half for a half-life. And so you'll kind of see down here, I've got a couple of different versions of a formula. And so this notation is commonly used for doubling time questions or half-life questions. You don't have to use them. So again, you can use this basic formula and you can calculate a growth rate per 1 year, or you can keep it as a doubling time, but then your exponent is going to not be a whole number, it's going to be a fraction, because that is that proportional change per year. Okay, remember I said over here it was a proportional change for a specific time period. I'm saying per year, but again, it could be per hour. So I'm going to work with this formula or this formula just today, but I will show you what I mean by if you don't like the formula and you want to have an exponent that's a whole number. I'll show you one example of how you could do that. And some people are going to choose to do it with this formula and others will choose the other one. You're going to get the same answer no matter what, okay? So just understand this is just a special case of exponential growth or a special case of exponential decay, okay? All right, so here's a very common example. So a culture of bacteria is doubling every 4 days. Okay, so that's all we know. We don't know the daily growth rate. We just know that every 4 days it doubles in whatever it was. So if they're telling us that initially on whatever day this was, something had 100 bacteria present. So let's think about that. So let's say today, whatever today is, there's 100 bacteria present. Okay, so initially I'm going to say that on day 0, if there's 0 bacteria. Now, after 1 day, I don't know how much there is. After 2 days, I don't know how much there is. After 3 days, I don't know how much there is. But I do know on the 4th day, my bacteria has doubled. So right now, I can put 200 in here and know that that's how many bacteria I have on day 4. I could do this again for day 5, day 6, day 7, but on day 8, I know for a fact it's going to have doubled in value. So my bacteria was 100 initially, 4 days later it's 200, 8 days later it's 400, and this is exponentially growing. 1, 2, 3, so 9, 10, 11, boom, and I can continue this pattern forever. okay, dot, dot, dot. Now, like I was saying, you can spend some time and try to figure out, okay, well, what's the growth rate per day? But that's not necessarily what I want to know. I can use my doubling time formula to estimate how much bacteria I'm going to have on day 20. So day 20 is going to be like way over here somewhere. Okay, and I can use this pattern, but what if day 20 doesn't happen to fall on exactly a doubling period? This one actually conveniently does, right? Because 4 days after 12 is 16, and then 4 days after 16 is 20. So I actually already know this answer because at 16, I'm going to be at 1600, and then at 20, I'm going to be at whatever double 1600 is, which is 3200. So I actually already figured out my answer to part B just by counting. What if I asked you for, well, how much bacteria was there after 18 days or after 6 days? And again, okay, well, 6 days happens to be exactly halfway. And you can do this deduction by counting, but if you wanted to use an actual formula, let's see how we can use that doubling time formula, okay? All right, so the formula that I gave you that you're going to use is, if you want to use it, is the A equals the initial amount, so the A naught, and I'm going to use doubling time to the exponent of some time divided by the doubling period. So that's your proportional exponent, okay? If you use this formula, your A is still your future value. So what do you have in the future, which is what we're trying to solve for. So that's our 20 day. I don't know that right now. But A naught is the initial value on the day that this started. So we knew there was 100 bacteria initially. So I'm going to put 100 in here. We know that it doubles. And what's its doubling period? Okay, so they told us it is every 4 days. So this 4 days is my D. Okay, I'm going to put 4 in here. And proportionally, for every 1 day, how many doubling periods have passed? So I can put T over 4, and that's basically my exponential function that models the situation. So that's my answer to part A. Okay, that's my formula that models a situation where T is the total number of days. Oh, and I should also point out, notice that the doubling period is given in days, and the question is also asking you for something in days. So because the units are the same, we don't have to worry about anything. We can just plug in the 4 and the 20. Okay. Now remember how I said earlier, we could actually have counted how many doubling periods happened until you got to day 20. So you could count. Well, here's doubling period number 1. Here's doubling period number 2. 4 days later is doubling period number 3. At 16, we had doubling period number 4, and so at 20, we had doubling period number 5. Well, look at that in the formula. If I take this formula and I put in 20 for T, I found out that there's exactly 5 doubling periods that have happened since the initial start. And so this becomes 100. How many times did it double? 5 times, because 20 divided by 4 is 5 times. What's 2 to the exponent of 5? 32. And what's 32 times 100? And so putting this all into our calculator, we're going to get that 3200 that we already knew because we could count just by looking at the timeline. Okay, so 3200 bacteria are going to be present. Bacteria exist after 20 days. Okay, so that's sort of what we're thinking of. If I had asked for, I mean, we don't want to have to sit there and count and say how many doubling periods are there. What if they asked me after 4 years? Oh, okay, well then we got to figure out how many days there are in 4 years, figure out how many increments of 4-day periods there are. And again, that becomes tedious when we're trying to kind of figure it out with a timeline. So a formula is a lot more effective. Okay, now I wanted to show you sort of actually going to just double page this for a second. And I just want to show you an alternate way you can look at this. So right now we've got a formula that looks like this. A equals 100 times 2 to the t over 4. Now, remember your exponent laws. We did this actually before March break, so hopefully you remember that we could actually use our exponent laws to break this formula up, this exponent, this power up. And so I can write this as 2 to the 2 to the t over, so if I wanted to bring the quarter in to the t, okay, so all I did was just break up that exponent and wrote it a little bit differently. Now, what is the 4th root of 2? So if I write using my radical laws, so that writing this as a radical, remember we did this before, so this is the same as this. Do you agree? I hope. Okay. So what I've done is I've broken the power up so that now look what you have. Now you have that whole number exponent. So if you really don't like having a rational exponent, then break it up into 2 parts. Now guess what this right here represents? If you take the 4th root of 2 and put that into your calculator, that's going to give you approximately, I'm just going to do that right now quickly here. Looks like 1.19 to the t. Guess what that number is? That is your growth factor. That's your B value. Okay, so B is 1.19. That's your growth factor. So from a previous day, 1.19% increase every time. So what is that as a rate? Remember the B is equal to 1 plus the growth rate. If I subtract 1 from that, 1.19 minus 1 is equal to my rate. That gives me 0.19%. Multiplied by 100, of course, and you get percent. So therefore, if I asked you, what's the growth rate per day? Not every 4 days. I know it doubles every 4 days, but what is it? How does it grow every 1 day? You can say that it has a 19% daily growth rate. And that's your growth rate daily. So if you just kind of go back to the little chart I started off over here, that's basically saying, let's come to page 1 here, if I multiplied 100 by 1.19, then I could have calculated 119. I would have known that I had 119 bacteria on the 2nd day. If I multiply that by 1.19, I'm going to just do that on my calculator here, times 1.19, you get about 141.6. So on day 3, I had 141.6. If I keep multiplying by 1.19 every time, by the time I get to the 4th, I'll get to 200. By the time I get to the 8th, I'll get to 400. By the time I get to the 12th day, I'll get to 800. So we could have done this to calculate our daily growth rate if we really wanted to, but it wasn't necessary. If I just wanted to know something in the future, I could have used the doubling time formula and just predicted something based on that. Okay, I hope that you can kind of see that there's 2 different versions of how you could have done the question. So in general, let's open a second page here. So in general, if you either could have used this formula, A naught, and then you could, instead of having a 2 inside, you could have taken the dth root of 2 and raised it to an exponent of 10, because that's coming from this formula here, A naught 2 to the t over the doubling time, right? And so using that formula, the radical rules, I could have split this up. into A naught 2 to the 1 over D all to the T. Okay, I hope you see that. I don't recommend doing that. I don't do it that way. I just use my Dibbling time formula and I work with that. Okay. All right. So I'm going to just jump back here for a second here. So that was our first example. There is, I'm not going to do all of these for you. I think I have posted the written solutions. I think once I've showed you a doubling time and a half time question, you should be able to do them all. I just wanted to point one thing out for the next example. This is what I was talking about earlier. The doubling period on the second question is 10 hours, but I'm asking you how much bacillus I'm going to have, how much bacteria I'm going to have after 2 days. So just please make sure if your doubling time is given to you in one set of units, like hours, you must convert your 2 days into, in this case, 48 hours. You can't use the number 2 in your formula. It has to be all consistent with units. Okay, so I'm going to let you do number 7 on your own. You can check your answers on my posted solutions. But I want to do a Halflife question. So let's do number 8 right now on your examples. This is your half-life of marijuana in your bloodstream. So basically what it's saying is if you had some marijuana in your bloodstream after exactly 1.5 days, or I guess approximately 1.5 days, you will have half of that amount in your body. Okay, so if somebody took some marijuana for medicinal purposes 9 days ago, how many total half-life periods have passed since they used marijuana? And then what percentage can I assume would still be in that person's bloodstream after that 9-day period? Okay, so you kind of answer that question all at one shot with the formula. So this is my half-life formula. So my half-life formula is very similar to the doubling time formula. It's still A naught, but instead of a 2, it's a half. And then it's still T, but instead of I'm just for convenience, I could use D if I wanted to, but I'm just going to use H because H stands for half-life. Okay, so now again, if you really don't like using my formula, if you really don't like using this formula and you want to have a whole number exponent, by all means, the revised version you would be using is A naught and then A naught. And now you're going to have, I think this is uglier, but you're going to have the H root of a half all to the exponent of T. So there's your version if you wanted a whole number exponent. I'm not going to do that one. I'm going to do the half-life formula. Okay, so first question is just basically saying how many half-lives have passed. So they're just basically asking you for this. If 9 is my time in days and H is my half-life, which is 1.5, what's 9 divided by a half? That's what they're asking. Okay, so I'm gonna answer both A and B in the same. I started with how much? I started with oh, you know what? They didn't actually give us a quantity. Oh, this is good. They didn't actually give us a quantity. I'm just reading the question saying, how much did they take 9 days ago? If we don't know what they took 9 days ago, then what you're going to do is you're actually just going to assume it's 100 because this is a percentage, basically, right? You can treat this as 100%. So if you think about kind of what I was doing with the timeline, today on day 0, I have 100% of marijuana in my bloodstream. After 1 day, after one, actually these are kind of half days. So after one, actually make these halves. So after half a day, after 1 day, after 1.5 days. So now at 1.5 days, I have 50% of the marijuana in my bloodstream. And then 2 days, 2.5, 3 days later, so 1.5 more days, I'm at 25%. So this is kind of sort of a visual of what's happening. Okay. And so what we're saying is if we started at an initial value of 100%, and how many half lives have passed? So T is 9 days. a half-life is 1.5 days. So a total of 6 half-lives have passed after 9 days, right? Because here's 1.5 days, here's 3 days. I got to do that again, 4.5, and then 6, and then 7.5, and then 9. So I can count if I wanted, or I can just figure out the proportion using the formula, and I can calculate that there was 6 total half-lives that passed. There's my exponent of 6. And now I'm just plugging that into my calculator. So 6 half-lives have passed. I'm going to put in a half to the exponent of 6 and multiply by 100. So I'm going to say, just did that on my calculator quickly here, 1.56%. So even after over a week later, 9 days later, I would still actually have 1.56% of marijuana remaining in my body, if that was actually, in fact, the half-life of marijuana. Okay, so that answers A and B. This is the amount, or the percent amount, percentage remaining. Okay. I hope that makes sense. If it's confusing at all, please come see me during office hours. I can walk you through it a little bit in more detail. But I hope that helped. Okay. I want to do one last question, because sometimes you're not going to be given the half-life, and that's what you're asking for. So I actually used my son's brain injury example for this this number 9 example. You know that he has a brain AVM, and he had gamma knife radiation done. And so a gamma knife radiation specialist, his doctor, gave him 480 milligrams of a radioactive substance to treat his AVM. So he was injected with that in his brain through surgery. And after 24 hours, 30 milligrams was left in his brain. So my question to you is, what is the actual half-life of this radioactive substance? So now I'm asking you for the H. Think about the equation. Let's just plug it in right now. I'm just going to use blue for this case. Okay, so A is the initial amount, A naught. We're looking for a half-life, so I'm going to use the half-life formula. And it's some amount of time divided by some given half period. So H is actually what I'm solving for. So let's fill in what we know. We know that he made 480 milligrams, but only 30 was left. So the 30 was left in the future. So that's why I'm going to put 30 in for my A. The initial amount he was injected with was 480. Don't put your units, by the way. Notice I'm not putting mg. Okay, so here is the information so far I know, but I had the 24 hours. Now, they didn't tell me anything about half-life. They didn't tell me my half-life had to be given in days or weeks or minutes. So I can treat T as being 24. But if they wanted the half-life, if they specifically said what is the half-life in days or in minutes, you would have to convert 24 hours into that set of units. Okay, but we're going to keep it as 24. So there's my formula. Now let's remember how to solve for an exponent that is a variable. So this is going back a little bit to a previous unit where we're going to solve for an exponential equation. So SAMDAB tells me to isolate first the term that has the exponent. So this 480 is in my way. So I'm going to divide both sides by 480 to start with, because that's multiplication. Right? So again, I'm just using SAMDAB, which is the opposite of BEDMAS. So multiplication comes before the exponent. So I'm going to do the division first. 3480s is basically 1/16. So 1/16 is equal to 1/2 to the 24 H's. Now, there are a couple of ways you can do this question. Okay. Personally, I don't work with decimals if these numbers are nice and easy. And these are easy because I'm dealing with 2 at the bottom and a 16 at the bottom. So 2 and 16 are nice numbers to work with. If they were not nice numbers, then please, by all means, definitely use decimals. Now, I'm going to show you the grade 11 way, and I'm going to show you the grade 12 way. And I have showed you this before, so this is a little bit of review. To do it the grade 11 way, what you're trying to do, we learned earlier in the year that if we had a power raised to an exponent equal to another power that had the same base raised to another exponent. Doesn't matter what variables I use. If those powers were equal to each other and the bases were the same, then remember we were able to just drop our bases and equate our exponents. That's my grade 11 mission, okay? I'm trying to get this base and this base to be the same. So 1/16 needs to be written as 1/2. I want that to have the same base. Well, I can't just change it unless I put an exponent on that 1/2. So what does 1/2 need to be raised to the exponent of to give me back 1/16? So if I squared 1/2, I'm only going to get 1/4. If I cubed 1/2, okay, so what I'm doing is I'm just doing kind of trial and error, and I'm guessing what number does I have to put up here. If I cubed 1/2, that's 1/8. That's not 1/16. Oh, but if I put a 4 up here, then 1/2 to the exponent of 4 is in fact 1/16. Now I've got two powers on either side of the equation that have the same base. So what am I allowed to do? I'm allowed to cancel out my bases and equate my exponents. And there we go. So that's the sort of grade 11 trial and error way. You're just guessing and checking. In this case, and most of these cases, by the way, you will get nice, easy numbers to work with. So it shouldn't be necessary to do the grade 12 way that I'm going to show you in a second. And now it's just a matter of cross multiplying and again using SAMDEB to solve. So 4 h's is 24, which means h is 24 divided by 4, which is 6. Okay, so just dividing both sides by 4. So what does that mean? H is 6. H was the half-life. So every 6 hours, the amount of radiation will get cut in half. That's what we just found out. So therefore, the half-life of this radioactive substance is 6 hours. So every 6 hours, my amount's going to cut in half. Sorry, my pen, my pen is so crappy. Okay. All right, so that's basically how I would expect you to do it in grade 11. If you wanted to, you could use logs. And so option two is basically, actually it should have started from here. Option 2, and I'll do this in green, is where you would log both sides. So you would log 1/16 and you would log 1/2 to the 24 h's. And then one of the rules I showed you before was the reason why you'd log both sides is so that you can bring your exponent down and it comes in front of the log expression. So 24 divided by h comes in front of the log of 1/2. Okay, and now it's just a matter of dividing both sides by the log of 1/2. Divide this side by log of 1/2, and guess what happens when you divide log of 1/16 divided by log of 1/2. And so what you should get is exactly what we had before. So if you log 1/16 divided by log of 1/2, you should get back 4. So this should be 4. And then that's equal to 24 over h. And now you're basically right here at the same step we were at before. So by logging 1/16 and dividing it by log of 1/2, you will get back that trial and error number that we had to do. And then, of course, you're just going to get your h is equal to 24 h. Okay, so you're going to get the same answer. It's just whether or not you want to do it by trial and error or by using logs. And like I promised you, you will get numbers that are easy. It shouldn't take long to do trial and error. And you don't have to worry about calculator work. Okay. All right, I'm going to stop there. There are a bunch of other questions I want you to practice. So with doubling time, it's giving you a doubling rate here. This one here, you're estimating the half-life is basically what we just talked about. Because if you're using the grade 11 strategy, you're technically not exactly finding the half-life. And then there are a bunch of practice questions that I'm going to ask you to try. Okay, so good luck. Come find me during office hours if you need any other help.